We've spoken about sequences. We've spoken about functions. We made a link between functions and sequences. The next natural step is to extend these notions and to start talking about sequences of functions. These arise surprisingly often in analysis environments. We're going to start by talking about the two types of convergences or sequences of functions. So when you have sequences of numbers, there's only one way in which a sequence can converge. It might not converge, but if it does converge, it only converges in the same way. But functions actually introduce an extra degree of freedom, an extra dimension along which they can converge. So let's talk about this for a second. Throughout, we'll let A be some subset of the real numbers R. Fn, written like this here, is a sequence of functions from the domain A to a set of real numbers. If you pick any x in A, the sequence of functions evaluated at x is actually a sequence of numbers. Notice the difference here. For some x, this sequence might converge. For others, it might diverge. When it does converge, the limit has to be unique. Again, remember, when I write fn at x, I mean the specific value that the function fn takes on at x. So here I am talking about numbers. Well, the value to which the limit converges depends on x. If you look at all of the values for which this converges, so if I look at this function f here, f, which goes from a to r, to each x you associate the limit. These values, we will say, on this function f, we call it the pointwise limit. Of the sequence of functions f at n. And we will typically write this thusly. So we are, roughly speaking, making the assumption that we only care about these points where the limit converges. So the domain A here would be the set of points in the initial A where the sequence of functions converged pointwise. So this is our new A. Let me just reformalize that. Fn be a sequence of functions let A0 be a subset of A, and f be a function from A0 to R. We'll say that the sequence Fn converges pointwise to a function f on A0 if, for every x in A0, the limit when n goes to infinity of fnx is equal to f at x. And as I said, we would denote this by so this is the formal definition. A few examples here. Consider functions f at n, which are defined by the following rule. Fn at x is going to be x divided by n. Let's look at at the potential candidate limit f at x, which is equal to 0, then we would say that Fn converges to f on R because the limit of n goes to infinity of x divided by n is equal to 0 for every x. That has to be shown or proven, but you know, if you think about this, according to the rules of the limit that we've seen, x is a constant with respect to n here, so this would be x times the limit n goes to infinity of 1 over n, assuming that each of these limits exists, and it does. It is indeed 0. Here's a slightly more interesting example. Consider the following functions. X to the n. Look at those over the interval -1, 1. Now, do we know what these functions look like? If x is equal to 1, what I have here be this one, x to the 1. If x is equal to 2, oops, not very well drawn here, but this is the parabola, f2. If x is equal to 3, this thing. If x is equal to 4, this thing. So what are we noticing? Let's do another one just for the sake of it. X is equal to 5. For every point, so I'm going to take this point right here, I'm seeing a sequence of numbers which is alternating between positive, negative, but which is getting closer and closer into 0. Every point here as well. Right? Eventually gets closer and closer, converges to 0. On the positive side, the points stay positive. They get closer and closer to 0. At 1, well, all the functions here go through the point 1, and so the sequence of points is always equal to 1. The only place where something is weird is here. The points alternate between -1 and 1. Right, so what we're seeing here is when x is equal to 1, the limit of x to the n when n goes to infinity would be the limit when n goes to infinity of 1 to the n, which is 1. When x is between -1 and 1, the limit when n goes to infinity of x to the n, 0. All of these points eventually get there. It gets there differently depending as to whether x is positive or x is negative, but the limit still goes to 0. When x is equal to -1, then the limit here does not exist. Right? Because it alternates between -1. So these functions here, perhaps initially they were defined on the closed interval -1, 1 to r, although to be fair, they're defined everywhere, not just on the interval -1, 1. They're polynomials, but we're just going to restrict it to that point. And even if we define them on -1, 1, it only makes sense to speak of the limit over the interval excluding -1, which is this function there. What we've shown is that Fn converges pointwise to f on the interval open -1, closed 1. That is, if you buy my argument. Well, we know that this limit is 1 for sure. This is something you have to show here, presumably. That's not too difficult to show that. You'd have to use a definition. We do have a candidate for the limit. So in effect, here you're supposed to say, for every epsilon greater than 0, there exists an n epsilon equal to, well, we don't yet know what, but we'll be able to find it using the Archimedean property such that xn minus 0 is smaller than epsilon whenever n is greater than n epsilon. The thing you'll notice is that this n epsilon actually depends on the value of x that you've selected. So it's not just n epsilon, it's an n epsilon x. And it makes sense, right? If we are very close to the origin, it won't take long for x to the n to be close to 0. If we're very close to 1, it may take us a number of iterations before the values actually do get close to 0. So the number of iterations that we need depends on the value of x that we have. Here's a remark about the sequence of functions. Each of the x to the n's here are continuous on the interval -1, 1. But the limit is not continuous. So that's a bit of an annoyance, right? We have continuous functions, which we think play a very crucial role in building analytical reasonings. We have a limit of functions which exists, but the limit of continuous functions is not continuous, or not necessarily continuous. In this case, it is clearly not continuous. There's something there that is bothersome. And this is why there are two types of convergence for sequences of functions. But we bother with the second type of convergence. We would really like it if the limit of continuous functions would be a continuous function itself. So we need a more important type of, a more restrictive type of convergence for that to be the case. Look at another example of functions that are defined according to x squared plus mx divided by n. And the function f, the candidate for the limit, to be the function x. Well, look, f(n) of x, you can rewrite this as x squared over n plus x, and that, when n goes to infinity, goes to x. So we'd say, yeah, sure. These fn's converge pointwise to f on R. Here I had continuous functions. My limit x is also continuous. It's still possible for a pointwise limit to be continuous if the sequence of functions was a sequence of continuous functions. It's not always going to be this continuous function, but we'd like some way to guarantee that it's always going to be continuous. Enter uniform convergence. Consider the sequence if it then converges uniformly to f on a subset A0 of A. And again here, even though I haven't explicitly written, we are assuming that these fn's are functions from A to R. If for every epsilon greater than 0, there exists a k epsilon, and here I'm explicitly noting that the dependence is not on x. So this k epsilon is independent of the choice of x, such that the distance between fn at x and f at x is less than epsilon whenever n is greater than k epsilon and x is in the subset A0. We would denote that by using the double arrow. Fn converges twice to f on the set A0. Well, clearly from this definition, if you have uniform convergence on some set A0, you also have pointwise convergence A0. This definition here works as well for pointwise convergence. It's just that in pointwise convergence, it's conceivable that this k epsilon here will depend on x. What we do not have is the contrapositive. And we have a counterexample here. The sequence of function f at n converges pointwise to f, but it does not converge uniformly on f, because the definition here, the integer n epsilon or k epsilon as the case may be, is dependent on x. Look at an example. Look at the functions that are defined according to this rule here. Sine of nx divided by nx. And the candidate for the limit will be a function which is 0 everywhere. Well, it's 0 everywhere, but let's just restrict this to the interval 1, 2, so that we don't divide by 0. Right? We let epsilon be greater than 0 and pick an integer k epsilon, which is greater than 1 over epsilon. We know this can be done by the Archimedean property. What do we have then? Whenever n is greater than k epsilon, we have the value of the function fn at x, sine of nx divided by n times x, minus the value of the candidate limit function at the same x. Well, that's always 0, so equal to 0. That is going to be sine of nx divided by nx. Sine of nx in absolute value is always smaller than 1. And here we're left with nx at the denominator. We can get rid of the absolute values because x is in the interval 1, 2, hence positive, and n is an integer, also positive. So the absolute value of sine nx divided by nx minus 0 is always going to be less than or equal to 1 over n times x. Now our values of x are always between 1 and 2, so x is always greater than 1. So 1 over x is always smaller than 1. 1 over 1, which is 1. So this is going to be less than 1 over n, which will be less than 1 over k epsilon, when n is greater than k epsilon, which is less than epsilon. There's the end of the proof. So our ability to say that these fn's converge uniformly to f on 1, 2 hinges on the ability here to take this nx, which I could have written this way, in our sequence of inequalities, and to remove it altogether because we had some information about where it resided, right? We knew that x in absolute value was always going to be greater than 1 here, and smaller than 2. In particular, that 1 over the absolute value of x had to be smaller than 1, greater than 1 over 2, it insists. We use the second half of the inequalities. But that was a crucial part. We could remove the x's altogether from here, and hence our k epsilon didn't really depend on the value of x that we were using. Let's do one last example. There are sequences that converge to f on A0, but that do not converge uniformly to f on A0. When I don't specify the type of convergence, you only assume that the convergence is pointwise. Right? Uniform convergence is a stronger version, and so that's the one we qualify. I have said that this is the case. I've shown you the example. Let's actually look at the example in more detail. So we had these functions fn from -1 to 1 into the set of real numbers to each x. We associate x at n. We have the candidate limit f from the half-open interval -1, 1. It's closed. We've illustrated, if you want, that the convergence was pointwise, so we know that this is true. Now let's look at the definition, right? We'll show here that the convergence cannot be uniform. How do we do this? Well, we need to negate the definition of uniform convergence. So fn does not converge to f uniformly on A0 if you can find an epsilon greater than 0 together with a subsequence fnk of the initial sequence fn and a corresponding subsequence xk of numbers here, values in the domain A0, such that the distance between xk evaluated by the function f at nk minus f at xk will be greater than epsilon 0 for all k and n. And what I suggest you use here is the following xk. You can use nk to just be n. So the subsequence in question will be the actual sequence itself. And so what we're looking at now is this quantity here. Well, fk of xk will be, according to this, xk to the power k minus, now with xk in question, is not equal to 1, right? The xk is 1/2. So this f at xk here will be 0. That leaves you with 1/2 to the power 1 over k. It's xk to the k, which is 1/2. Just need to pick an epsilon 0 for which this is true, such as 1 over 4, say. This isn't saying that the values of fn at xk don't eventually go to 0, but they don't go to 0 according to the uniform convergence definition.